Okay, so like everyone else, I have to thank Michael and Alex and the other organizers for putting this together. I came at the very beginning of the program for 3 weeks, and it was fantastic. I really appreciated the opportunity to meet this community and integrate myself into it a little bit. So I'm going to talk about something that is a little bit on the more methodological side, but I think what motivated us to start thinking about these problems is actually related to controlling self-assembly. So we have started asking a lot of questions about non-equilibrium control and self-assembly, and this is a topic that I've been working on for 5 or 6 years, mostly in the context of non-equilibrium systems that have some sort of really far from equilibrium behavior like active matter systems. And one of the key questions that we've really started to think about and contend with in non-equilibrium physics is how do we actually produce analogs of things like free energies for non-equilibrium systems? How is it that we actually understand the probability distribution of various observables? This is very much like what David Limmer talked about. He was using this sort of variational large deviations approach, which is a technical term of art for basically computing averages in these types of systems of observables that depend on dynamics. So we have developed strategies for doing this sort of thing to map out non-equilibrium phase diagrams and produce structures like the one seen here, where you have active particles that self-assemble into things like colloidal crystals. And these require basically arbitrary control over the system. This is much like what David was talking about, where you're actually tuning the parameters of a force field or something like that. That's a useful computational tool in many different settings because it actually tells you what sorts of things are possible if you were able to actually tune those interactions. But in many cases, the types of perturbations that we could do to a system that is assembling would look much more violent and much more generalized, much like what Rob was mentioning earlier. In most cases, we don't actually have arbitrary control. We have some sort of way of coupling into the system that's actually much less precise and more constrained. And so what I've been working on and trying to understand is basically what are the limits and possibilities in a context where what you control is much less precise. So in many cases, that will be something like coupling to the temperature or an electric field. Or in this case, something like an active system where you could spatially pattern, an optical perturbation to drive activity in a spatially localized way. And you can ask questions like, how well can I control clustering? Can I get monodispersed clusters of these active colloidal crystals? And indeed you can, but you pay a cost in the amount of work that you would have to do for that. So that cost is quantified by one of these sort of generalized non-equilibrium results of the type that we've already seen in this conference and that are kind of ubiquitous in non-equilibrium stat mech, which is that the accuracy of my control, which here is just quantified by looking at the deviation from whatever target average property I try to impose on the system, is related to this thing that's called a Wasserstein distance, and that actually directly quantifies a cost in dissipation. So the energy that you dissipate is a bound on how precisely you can control the distribution. This is a fairly intuitive result that's basically saying that if I want to push a distribution into something that's far from its steady state, far from its equilibrium state, for example, then I will pay a cost that is proportional to how far I push it. Okay, so yeah, so there's actually a related result that you can derive directly from this, which is a sort of speed limit, which tells you that the cost that you pay in energy is going to be related to how fast you do this transformation. So this distribution you can think of as going between two steady states, but it is always in a finite time. So it's a truly non-equilibrium result, and it's something that is actually fairly powerful from that perspective. Of course, all of these optimization strategies, these sorts of things, they're pretty confined to relatively simple models. And, that's something that I think a lot of computational people will sort of, throw their hands up and say, okay, but this is what we can do. And I find that to be a little bit unsatisfying. So we started trying to revisit how we actually build and think about these models to try to improve the state of the art in that direction. Okay, so just to mention, the way that we actually do these controls requires relatively fancy deep learning strategies, but that's something that you can read about if you're interested or talk to me about. So, you know, obtaining robust thermodynamic or dynamical predictions for these models is going to require something better than what we're currently doing. And one of the things that, you know, I think we need to ask as a community is what would be better. And one of the, you know, the ideas that I think many people are tossing around right now is using generative models to sample configurations of physical systems. So generative models are, you know, primarily machine learning models, so primarily neural networks, that take as an input some noise, something that you can sample, and transform it into a distribution that is targeted, that is learned from data. And the examples of these are things that you probably are all familiar with. So large language models, like the general purpose transformers that have taken the world by storm. And the thing that we need to sort of contrast here is the reality of physical systems with the types of problems that we have, you know, in these sort of industrial applications. So the quantity of data that is used to train things like ChatGPT is essentially the entire internet. This is the sum total of human knowledge, and it requires a scale of computation that is completely inaccessible to the academic community. It's 1 million GPU hours. My NERSC allocation is about 5,000 GPU hours. Okay, so it's not something that I could do. And moreover, if you think about asking sort of physical questions, right, something for which you would want a statistical guarantee, in fact, there are none. So if, like me, you were sitting in the talks yesterday and wondering in Yvonne's talk, how do we talk about boojums? Like, what is the plural of boojum? You can ask ChatGPT that, and it will give you an answer, but there are no statistical guarantees that it's correct. So you should be careful what you say in polite company. Computer vision is a similar problem where there's quite a lot of data available, right? We have the total internet of images, right? And you can train these models on that. And the costs, again, are exceedingly large. And there are no statistical guarantees. And even things that are very well tailored and extremely successful deep learning applications, like AlphaFold, require data that's on a scale that's pretty unimaginable, right? I mean, this is using all of the sequence data that we have access to, all of the beam time of the last 50 years, right? The entire protein data bank. And the training costs are much more modest. The data set is smaller. But again, there's still no statistical guarantees. So we started thinking probably 4 or 5 years ago about how we could try to use generative models as a way of sampling physical distributions. And one of the constraints is actually a fairly technical one, and it's a constraint on the architecture of the models that you can possibly use. So there's a special class of generative models, which are called normalizing flows. And normalizing flows have this important property that they are invertible. So they're neural networks that you can invert the output and get back analytically to the original input. And if you want to compute a probability distribution, or if you want to, say, do Monte Carlo sampling and actually have the correct acceptance criterion, then you need that. That's a requirement. But of course, that requirement limits the expressibility of the networks. And so when you use these models, and often they're sort of benchmarked on these really simple systems, they actually produce something that looks like a deterministic flow from one probability distribution to another. So you sample a Gaussian distribution, you transform it under this map, and you obtain something that has more structure. These models have a problem, which is that if you have a limited data set, they experience this behavior which is called mode collapse. Mode collapse means that wherever you have data, all of the probability is going to concentrate on that. So when you train the model, you obtain one structure, you know, one conformation of your protein, for example, and you're going to sample that conformation over and over again, and you're never going to discover the other modes. So you're not going to discover anything with this if you use it naively. And if you have the right data, maybe not much of it, but you have data that's representative of all of your modes, then you can actually train these things to sample between modes, and that's a strategy that is actually very useful in a lot of different contexts, including ones that are interesting to, you know, to the community working on nanoparticle assemblies, because you can do things like compute absolute free energies or compute free energy differences between two different crystal structures in a way that's extremely direct because you can sample both of them simultaneously. And so this is just showing it for an atomic solid. And you can train these models very efficiently because we actually know in a pretty precise way how to choose the measure that we sample, the base distribution that we sample. And you can get things that sample every time something that is accepted and sample it extremely rapidly. And you can see, I mean, just from looking at the picture, that we're sampling configurational space for this low temperature solid much more efficiently than if you were to do a local Monte Carlo strategy. So, you know, this is something that I think has applications, it has legs, but, you know, there's still many different constraints that we actually encounter with more complex molecular systems with soft and local interactions. So engineering this distribution that you sample from and transform with a neural network is not typically easy. And so you can see here that we actually get, you know, with very little sampling, a very accurate estimate of the absolute free energy, one that requires much more data for other methods. Okay, so one of the things that we started thinking about is, you know, whether or not we can augment these types of models with coarse-grained models. So if we can sample a coarse-grained model where we actually have a physical distribution where we, you know, do normal coarse graining, but then use that as sort of the basis for transforming back to the atomistic structure. Okay, so the thing that we would like to be able to do is take coarse-grained simulations and recover the underlying molecular structure from them. So that's the strategy that I want you to keep in the back of your mind as I walk you through this. But you know, part of the problem that I sort of had when I started thinking about this is that I was trained as a sort of top-down coarse-graining person, right? I think of coarse-grained models as being useful only when you can take an experiment and build a model that recapitulates the features of that experiment in a way that's truly minimal. However, you know, there's a huge community of people that have quite productively used bottom-up coarse graining where they start with an atomistic simulation and they build a coarse-grained model that is thermodynamically consistent in exactly the way that Marilyn was describing. And they use those very productively in many different contexts. Of course, there are problems with it, and so I want to walk through those problems just so that we can think about them collectively. The first one is that you have to make a choice of the representation that you use when you build a bottom-up coarse-grained model, right? So we start with an atomistic structure, and generally we make a relatively arbitrary choice of what the thing we're going to map it to is, right? So we choose some beads to represent our underlying atomistic structure, and that choice is, you know, is not one that's optimized typically. It's almost always a linear projection. It's independent of the fine-grained state. There's nothing that says that you need to coarse-grain, you know, two different conformations of a protein in exactly the same way. The relevant degrees of freedom may be different in different conformations. And the potentials that are typically used now, you know, people are much more frequently using machine-learned potentials, but typically they were just completely empirical, right? It fit with a small number of parameters. In addition to that, once you actually have this coarse-grained model, you have an interpretation problem. And you know, at some fundamental level, I'm still a chemist, and I really, you know, I feel like I need information about the molecular structure a lot of the time. But when you look at these, you know, these bead and spring models, right, that you get from coarse-grained modeling, you lose insight into a lot of the underlying chemistry. And that makes it very difficult to recover the, you know, mechanism or other things that might be important for actually some sort of transformation. Moreover, the dynamics from coarse-grained models, as the question was pointing out, are often quite difficult to map, right? I mean, we don't have a systematic way of recovering dynamics much of the time. Okay, so finally, and this is the one that I consider maybe to be the most fundamental from the computational side of things, is that ultimately coarse graining is typically a boutique strategy. You do it for one molecule at a time, you do it for one system at a time. That's very data intensive. Often you do it for one temperature or one state space point at a time. And we can't, you know, take different proteins and use the same coarse-grained force field for them. And that to me is a sort of a problem that really needs to be solved in order to move forward with these types of models. So we need lots of data. We need all of this information. And then once we have the coarse-grained model, we can simulate it, but we can't actually feed that back into improving the models, right? The only thing that we can do is sort of post hoc checks where we compare with some experimental data or something like that, and then maybe change the strategy. But that's not really a closed loop. So we are aware of this problem as a community, right? There's a lot of work on each one of these topics. I would say the main thing is that there are very few integrated strategies trying to address them collectively. And there are very few statistical guarantees that the models that we produce from addressing these things are actually going to be robust. And what I mean by statistical guarantee is that I want to sample a Boltzmann distribution, right? I'm a stat mech person. That's the one thing that I care about, is actually getting Boltzmann statistics right. Okay, so all of that in mind, what we are going to try to do, and what my group has been working on for the last couple of years, is trying to come up with strategies to effectively close the loop on coarse-grained modeling. So in essence, what I mean by that is that we want to generate fine-grained structures that we can feed back into a procedure to optimize the model in the first place. And so the strategy is relatively simple, conceptually at least. So we start with our fine-grained structures, typically from MD simulation or something like that. We build a map, a coarse-graining map. So this is a neural network, and it's a nonlinear map. So we're going to do nonlinear dimensionality reduction. It's not just going to be a linear projection that you would see in a typical like bead and spring type coarse-graining. And we will use that to optimize a coarse-grained potential, which does force matching in the sort of typical strategy, right? So this is going to be like a sort of generalized standard coarse-graining. But then the sort of crucial element of this is that we can take those coarse-grained points, right? So we sample coarse-grained space. We can take those configurations, and because we're using this sort of nonlinear dimensionality reduction, we can't think of this anymore as a sort of, projection of our original system. It's much harder to interpret the coarse-grained space now, because what I've done is I've made it a nonlinear map from my original space, right? This is a transformation that's much more complicated. So I can't look at the coarse-grained simulation and say what's going on. We have to have a strategy of going backward from the coarse-grained space to the fine-grained structures. So what we do is we use those coarse-grained data points that we collect from sampling this distribution, this Boltzmann distribution in coarse-grained space, and we invert using strategies from generative modeling. So we invert using generative models that allow us to reconstruct the atomistic structure in a way that is actually statistically precise, in the sense that will give us a Boltzmann distribution. So all of these elements are learned, right? So this, in some sense, is a very sort of aggressive machine learning approach, right? We're learning the map, we're learning the coarse-grained potential, we're learning this inversion map. And so we have to optimize all of them, but in another sense, it's sort of a minimal use of generative modeling, because we have this big intermediate step, which is a much more classical step, right? This is something that we're really doing kind of typical energy-based sampling on. One that's consistent with the underlying atomistic structure. And so this is, something that is maybe using the generative model more decoratively, right? We're using the generative model basically to sample, but in a way that's very minimal. We're removing a lot of work from the generative model. We're putting all of that work into the coarse-grained model, which we know is good. And then the generative model just does this last step, which is recovering the atomistic structure. And there's an ensemble of structures that correspond to each point in coarse-grained space. So we use models that are actually, I would say, close to the state of the art for each of these different tasks. But it doesn't actually really matter which models we use. And of course, as the community evolves a little bit, we'll choose different models, because different models will be shown to have better properties, right? And so the framework is the important part. It doesn't really matter which models we use. The one thing that I think is actually truly important about the architecture in this context is having some amount of physics in it in order to, prevent behaviors that are going to lead to things that are, not rotationally invariant or not translationally invariant. We ultimately want these things to still have some underlying physics. And we have developed a few different strategies for doing that. We use now primarily these equivariant graph neural networks that were developed by Max Welling. And those have two of the ingredients that we want, which is translation invariance and permutation invariance. And then we use a slightly different scheme to get rotation equivariance, which just means that if I apply a force and I rotate that force, the force rotates, right? So that's an obvious property to want. And we do this sort of coarse graining step with actually ideas that came out of network theory. So if you have a social network, right, and you want to cluster groups, then you need to hierarchically coarse grain the network into nodes, and that's essentially what we use. It's a differentiable pooling strategy. So it's people at Facebook that invented these sorts of things because they want to figure out how to determine who your friends are. Okay, so when we do this step, we do give something up, which is that we don't have interpretability of the coarse-grained representation. So we can't look at the coarse-grained simulation and try to impute meaning into it. But we gain the ability to use these very, very flexible nonlinear dimensionality reduction strategies that are much, much more effective than just doing a linear projection. And it also has to change a little bit the way that we interpret the quality of the model. So the more conventional formulation of how you evaluate the quality of a model is you compare the potential of mean force, so the true underlying projected free energy, to this coarse-grained potential, right? So you compare this restriction of the Boltzmann distribution to the coarse-grained coordinates to the coarse-grained potential that you have. And you say, okay, if these two match, then I have the right potential of mean force. The quality of my model is good. What we do is something that we call weak thermodynamic consistency. Weak in the sense of weak convergence of probability distributions. It's actually a fairly strong constraint, but that's the nomenclature that I unfortunately chose. So what we actually check is that when we use our coarse-grained model and we invert the samples, we check that any average that we compute in the fine-grained space matches a Boltzmann average. Okay, so we want to recover for specific observables the fine-grained average in a way that's consistent with the Boltzmann distribution. So that's the requirement that we have. We get the right probability distribution in fine-grained space. So let me just show you a little bit about how this works. So the map that we use for the inversion, and so I'm glad that Chad brought up proteins several times because I'm going to talk only about proteins here. So we do this. We've done this for primarily proteins at this point. And when we sample the structure, what we do is we first reconstruct the backbone of the protein, and then we're going to hierarchically sample the side chains using these rational quadratic spline normalizing flows. Okay, so it's a mouthful, but basically what this is going to do is atom by atom, it's going to reconstruct all of the side chains of the protein in a way that is maximum likelihood with respect to the probability distribution defined by the Boltzmann distribution. And what we'll get is for each time we resample this configuration with a fixed backbone, we will reconstruct side chains that are slightly different, but are energetically very, very likely. And because these models are normalizing flows, what it means is that when we look at what's called the push-forward distribution, right? So we're sampling Gaussian noise, and we're transforming it with this map, this normalizing flow. When we actually want to know the probability of the thing that we've generated, we can evaluate it analytically because this is all explicit. The normalizing flow is invertible, so I know the inverse. And so I just ask, if I take my structure that I've generated, I pull it back under the map, so I invert the map, and then I just ask, what's the probability of this in the Gaussian distribution that I started with? That's the only thing that you need to know. And then you have the probability distributions, which means that you can Monte Carlo sample, or you can reweight them relative to a Boltzmann distribution. We've done both. It doesn't really change it whether or not you use reweighting or Monte Carlo, but both work. Okay, so this is what it looks like, right? It actually just generates out these side chains. The procedure is pretty straightforward. And more importantly, so this is just one example of a GIF of the same structure being generated over and over again. When you do this, you get structures that you can then put back into your data set, right? So you can start with actually a very modest data set. You have atomistic structures. You put them back, and then you just train in a loop, right? It's a closed loop now, so you don't have to, acquire more data to improve the coarse-grained model. You can actually use the coarse-grained model to improve the coarse-grained model. So it's a bit more unsupervised in that sense. Okay, so this is the hydrogen atom of molecular dynamics. So this is alanine dipeptide. It's a very minimal protein, and this is just showing that if you do this procedure, you can reweight relative to a Boltzmann distribution, and you get something that's quantitatively accurate on both large-scale properties. So we actually recover the free energy everywhere that we sample. Exactly. The error here is actually in the MD free energy, not in the coarse-grained free energy. So the regions of high error at the boundary of this are just regions that are undersampled by MD. The potential energy, for example, the distribution is quantitatively accurate, both in the mean and the variance, and same for small scale properties that we couldn't actually even access with the coarse-grained model. So when we look at things that just don't exist in the coarse-grained model, like bond angles, we get them quantitatively accurately as well. And you can do it for more complicated proteins, ones that have multiple metastable states and have complicated folding trajectories, right? So this is chignolan, which has a misfolded state, an unfolded state, and a folded state. We get quantitative accuracy on, again, large-scale properties like the potential energy, and small-scale properties like side chain fluctuations. And so what this suggests is that there may actually be a path forward in transferability of these models. So I'll kind of conclude with this. So what I want to point out is that this now actually gives us an opportunity to build truly transferable coarse-grained models, in the sense that if we consider things like intrinsically disordered proteins, which is one of the topics that my group is pretty focused on at the moment, and we look at their fluctuations, so these things are relevant in signaling, and they're not purely intrinsically disordered, they actually have some structure. We can actually build models that allow us to sample ensembles, dynamical ensembles, of many of these simultaneously by just looking at individual tripeptides and building coarse-grained models that are invertible with these tripeptide ensembles. So we can take an intrinsically disordered protein like this one, and we can sample all of the relevant side chains. And what's kind of remarkable about this is that if we do these tripeptide simulations, we get dihedral angles, for example, that are sterically occluded in the actual protein, right? So this is something, this tripeptide simulation has, this distal histidine angle that is not accessible to the underlying molecular system, right, to the underlying IDP. But when we sample the IDP, we recover the right distribution for the reconstruction, even though we started with something that's a little bit over complete. Okay, so I will end there. This will advance. Yeah, and just thank both the Department of Energy and Google Research for funding this work, and I'm happy to answer any questions.
Hi, Grant. Very exciting work. So I was just wondering if I missed something. So when you do the mapping back from the coarse-grained to fine-grained, did you say that it's not a unique mapping?
So for each coarse-grained point, there is an ensemble in the fine-grained space that corresponds to all structures that will map back to that.
Sure. So then my question is, how do you recover realistic dynamics if you're doing a sequence, coarse-grained sequence, but you're not getting a unique mapping back?
Okay, so this is actually a very complicated problem. I mean, the answer is the same as it is in regular coarse-grained model, is that you need to do Morris-Wanzig. We're trying to figure out ways of doing Morris-Wanzig better, but I don't actually think that anyone really knows how to do Morris-Wanzig in normal settings. So I think that this is a big problem, but yeah, I agree.
But you are using these to study dynamics?
Actually, everything that I showed you is just thermodynamic properties.
Okay.
I think in principle, we will be able to get dynamical information at some point, but we're not there yet.
All right, thank you.
Thank you for the talk. Wanted to ask, can you give us some estimate of how much computational speed up you get by coarse-graining in this way? Like if you would have just brute force MD, how much time it would take you to sample the same free energy landscape as it takes with your method?
So we have an estimate of this for chignolan. I forget exactly what the numbers are, but it's like roughly 100-fold. So we need much less data to build the inversion map than we would need from MD. And also, once you start, amortizing the data cost, once you start feeding the regenerated structures back into training, then you can make those costs look much better, right? Because you don't actually need to generate that data with MD. But I think that the true power of this will be in transferability. Right? I think for an individual model, it may be a lot of work, or if we have to do many different tripeptides, right, for example, to build something that's kind of more universal for proteins. It's the transferability, the fact that we can use one model for many different systems that would really provide the true savings, right? On the individual basis, I think it's not as dramatic.
If you compare this with Frank Noe's work on these Boltzmann generators.
So normalizing flows are Boltzmann generators, or Boltzmann generators are normalizing flows is the right way of saying it. So they have a mode collapse issue, right? So the data that Frank needs to train models for Boltzmann generators has to be so extensive that you can basically do PCA and then sample a Gaussian and invert a PCA transform. So it has this mode collapse problem. The paper that I mentioned at the beginning with Eric van den Eyden and Mary-Lou Gabriel is one that sort of analyzes the convergence properties of normalizing flows. And this is in PNAS, actually Frank edited it. And basically what it's pointing out is that this mode collapse problem is really profound. There are ways of addressing it, but for molecular systems, normalizing flows are very, very hard to use because they don't allow you to sample two different modes that are very, very far apart if the distribution is high dimensional in a way that's very efficient. That's why we use the coarse-grained model. The coarse-grained model basically allows us to mix between these modes, and then the reconstruction is a much easier task for the normalizing flow to learn.
And the coarse-grained model, you just use regular simulation. You don't do anything fancy like some umbrella sampling, etc. on top of it.
So we could do all of those things. Our coarse-grained models explore the phase space quickly enough that we don't need to. But if you needed to do metadynamics or umbrella sampling in the coarse-grained space, all of those methods are perfectly valid. The only thing that we need is that we sample a Boltzmann distribution with respect to the coarse-grained potential.
Thanks.
Thank you, Grant. That was a beautiful talk and work too. I want to go back where you motivated the use of going back from coarse-grained models to the atomistic models by retaining back the information at a less coarse level. And my question is, maybe you've addressed it, I'm not 100% sure, is that procedure would have meaning if it's unique. If you could, for every coarse-grained model that I give you, you can tell me what uniquely the molecular structure would be. But if it's not unique, and you can get from, now I know that going forward.
It has to be probabilistic, right? Because there's an ensemble of structures that will map down.
Exactly.
Yeah, so the map, I mean, the optimal transport, so the map that takes you from the coarse-grained configuration back to the fine-grained distribution, that map is unique. The map is actually, so it's a little bit misleading mathematically to think of it this way, but the map itself is actually going from the same space. So it has to be the same number of dimensions, the coarse-grained space, as the fine-grained space. I mean, we can talk about this more later, but that the maps themselves, you know, are there's a criterion to make them unique. But the point, I think, is that you need to generate an ensemble of structures, which is the Boltzmann distribution. It's all structures in the Boltzmann distribution that project under the coarse-graining map to the same point. So that's the map, right? That's the ultimate.
But they can refer to different, say, molecular systems in principle, these configurations, so you don't have identity of the.
No. So the ingredients of, like, you know, the atomistic characteristics, all of the ingredients in the system
would be the same from these different configurations.
They're the same.
So my question is the other one. So if I take, say, liquids and I map them onto a lattice gas model, I can map various different liquids onto the same coarse-grained model.
Right.
If I want to go backwards, how would I know?
So you need to choose which ingredient. I mean, maybe there's a way of sampling in a sort of alchemical way among all of these.
That's what I'm concerned about, the chemical ways.
Yeah, so in principle you could do that, but we impose the constraint that, you know, the ingredients, the molecular ingredients of the system are fixed. Yeah,
I got it.
Yeah,
okay.
But I think, you know, I don't see any sort of problem with formulating it that way. It would just be much harder to construct the maps.
Yeah, I have a similar question. I understand why you use a protein, because then there's no problems with distinguishability of the atoms. Is it easy or straightforward to extend these models to, for instance, simple Lennard-Jones system or colloidal system?
Yeah, so
where you have this n factorial, or how would you solve the n factorial problem?
well, so the coarse-grained model will have, some amount of the distinguishability contained within it, right? The actually challenging part of these models is constructing a map that's respective of, interactions that are not intramolecular. So if you have intramolecular interactions, that becomes more difficult. One of the things that we're working on is lipids, right? Lipids and other ligands for nanoparticles. And there, we have found so far that the strategy works pretty well, but you have to construct the map in a slightly different way so that you actually generate the structures in a way that's, that will respect the intramolecular interactions. So you need a model that's a bit more hierarchical, but it works for these sorts of systems as well.
So there's no problem with the n factorial that you can swap particles and you
No. So you would just generate. So I guess if you were to coarse grain away so many degrees of freedom that you had, many indistinguishable things that got collapsed into a single mode, then you would need to generate something that would also respect this. But the models that we use all have permutation invariance, so that's gone already. And there are other strategies like things that Frank Noe has used, like Hungarian algorithms, that address this in a very straightforward way. So I don't think that that's a fundamental problem by any means. But we haven't worked on it so much. Yeah.
So thanks, Grant. I have a question about the transferability that you emphasize a lot. Can you explain a little more? Because as I understand, what you learn from one protein, you cannot transfer to the other protein. Is that my perception correct or not?
No, we think we can. I hope we can. So, if you look at rotamer libraries of side chains for proteins, they're actually very highly conserved among many different proteins. So if you look at the different rotameric states of each side chain, so there's a pretty well-defined probability distribution for the types of structures that they adopt. That's coming from chemistry, right? So the underlying energy is such that there are only, a finite number of stable rotameric states for side chains, which means that if you actually had a model that, was sensitive to those distributions, right, knew about those distributions, then the thing that you actually need to capture on a protein by protein basis is just their interactions. And people have actually built force fields for proteins using rotamer libraries. So you can construct, a pretty realistic ensemble of protein structures from rotamer libraries. This is just, so that's just to emphasize that if you train models that generate based on those rotamer libraries, you can reconstruct protein ensembles very accurately. You just need to be very sensitive to the intermolecular interactions.
So I understand, but just to be a little more clear, so let's say that you have a protein and you have your coarse-grained model.
Right.
This coarse-grained model comes with certain parameters. Then you go to another protein. How much of this thing that you learn from this protein, with your method, you can automatically say, okay, I already know this. So you see what I'm trying to do?
Yeah. So the strategy that we have in mind is a little more targeted towards transferability than that. So we're not trying to take, one protein and then just apply that model to a different protein. What we're actually doing is we're fragmenting motifs of proteins and training models on those motifs. And then when we actually sample a large protein, what we're doing is we're building the model out of things that share those motifs.
So there is kind of a learning from each protein on these motifs. Is that kind of?
Exactly.
Okay.
Yeah. Similar strategies should work for lipids as well.
Yeah, so I have a question regarding the coarse-graining, or the degree of coarse-graining. So you said that, so normally when somebody coarse-grain a model, you have a choice of the degree of coarse-graining, right? That I guess in your language would be these linear models. But now that you're using these nonlinear models, it wasn't clear to me whether it's up to you to choose, roughly speaking, the degree of coarse-graining.
Yeah, we choose. I mean, we make a choice of, it works a lot like an autoencoder, if you're familiar with that. I mean, we compress the dimensionality to a tunable degree.
Okay.
And you know, the extent to which you want the sampling efficiency in the coarse-grained space to be high, and also recoverability of the fine-grained structure to be high, that's the trade-off, right? So you have to balance those two things. I don't have like a hard and fast rule for, you know, what those dimensionalities should look like. I mean, for alanine dipeptide, 2 is perfectly good, right? But those are the natural collective variables for alanine dipeptide. For chignolan or larger proteins that we've studied, you need more dimensions, but not dramatically more. 5, 7, yeah.
Thank you.
So I have a more or less philosophical question as an outsider. So as you know, one of the most beautiful results from statistical mechanics is renormalization and the universality classes. So what you describe here, like linking the coarse-grained level model to the microscopic details, does that can that be used in a way to help us understanding universality classes in non-equilibrium statistical mechanical problems?
I wish there were something that elegant in it. I mean, maybe something like that is possible. So I would say that, you know, the one thing that I always have to, you know, sort of remind myself with the renormalization group, though I love it, is that it's very, very specific to the critical point. And so, you know, you need the scale invariance of the critical point to actually get, you know, something that is kind of analytically coarse-grainable. Here, what we have is something that's much more statistical in the sense that, you know, we are losing information when we coarse-grain. We have to reconstruct that information with a generative model. And so, you know, the amount of information loss or things like that, I mean, we've thought about trying to quantify some of that using RG techniques, but I'm not sure that the analogy is perfect simply because, you know, the scale invariance at criticality is the thing that you exploit to be able to coarse-grain exactly. But most physical systems are not at criticality, and so we can't actually coarse-grain in a statistically exact way, right?
Yeah, that makes sense. Okay, if there are no more questions, let's move on to lunch. Thank you very much to all the speakers this morning.